Hey there, science fans! Have you ever wondered what makes our lights shine, our phones buzz, or our TVs come alive? It's all thanks to the amazing power of electricity. Electricity is like a hidden force, a flow of tiny particles called electrons that zoom around carrying energy with them. We use electricity every single day. Can you imagine life without it? No more scrolling through funny cat videos on your phone, no more listening to your favorite tunes on your headphones, and definitely no more late-night study sessions with your trusty lamp. Electricity powers our homes, schools, and cities, making our lives easier and more connected. But have you ever stopped to think about how it actually works? Let's break it down and explore the fascinating world of electrical circuits. First up, let's talk about electrical current. Imagine a river flowing downstream, carrying water from one place to another. In a similar way, electrical current is the flow of electric charge, those tiny electrons, through a conductor, like a wire. The more electrons that flow through a wire per second, the stronger the current. We measure current in units called amperes, often shortened to amps or represented by the letter A. Think of it like this: a small stream has a weaker current than a mighty river. Similarly, a low current means fewer electrons are flowing, while a high current means lots of electrons are on the move, carrying more electrical energy. Now, what makes those electrons flow in the first place? That's where voltage comes in. Voltage, also known as electrical potential difference, is like the pressure that pushes the electrons along the wire. Imagine a water tank connected to a hose. The higher the water tank is placed, the greater the pressure pushing the water through the hose. Similarly, the higher the voltage, the greater the force pushing the electrons, resulting in a stronger current. We measure voltage in units called volts, represented by the letter V. Just like you need enough water pressure for a good shower, you need enough voltage for your electrical devices to work properly. But wait, there's more! As electrons flow through a wire, they encounter resistance. Think of resistance as friction, or opposition to the flow of current. It's like trying to squeeze a large amount of water through a narrow pipe. It's going to be a tight squeeze. Different materials have different levels of resistance. Some materials like copper are excellent conductors with low resistance, allowing electrons to flow through them easily. Other materials like rubber are insulators with high resistance, making it very difficult for electrons to pass through. We measure resistance in units called ohms, represented by the Greek letter omega. The higher the resistance, the more difficult it is for the current to flow. Section 5. Ohm's Law, connecting the dots. Now that we've met our three electrical musketeers, current, voltage, and resistance, let's see how they're all connected. This is where Ohm's Law comes in, named after the brilliant physicist Georg Simon Ohm. Ohm's Law states that the current flowing through a conductor is directly proportional to the voltage across it and inversely proportional to the resistance. In simpler words, if you increase the voltage, you increase the current, but if you increase the resistance, you decrease the current. We can express this relationship with a simple equation: current I equals voltage V divided by resistance R. This equation is like a magic formula that helps us understand and predict how electricity will behave in different situations. Section 6. Real-life examples. Seeing is believing. Now let's bring Ohm's Law to life with some real-life examples. Imagine you're using a garden hose to water your plants. The water pressure from your tap is like the voltage. The amount of water flowing through the hose is like the current. The width of the hose is like the resistance. If you increase the water pressure, more water will flow through the hose. If you use a narrower hose, less water will flow, even if the water pressure is the same. Similarly, think about a dimmer switch for your lights. The electricity supplied to your house is like the voltage, which remains relatively constant. The amount of electricity flowing through the light bulb determines its brightness, representing the current. The dimmer switch controls the resistance. When you dim the lights, you're increasing the resistance, which reduces the current flowing through the bulb, making it less bright. Section 7. Safety first. Electricity can be dangerous. While electricity is incredibly useful, it's important to remember that it can also be dangerous if not handled properly. Always remember these safety tips. Water and electricity don't mix. Never touch electrical appliances or outlets with wet hands. Don't overload circuits. Plugging too many devices into one outlet can cause overheating and increase the risk of fire. Be careful with cords. Avoid using damaged cords or running them under carpets, as this can be a fire hazard. Call an electrician if needed. If you're ever unsure about any electrical work, it's always best to consult a qualified electrician. Remember, safety always comes first. Section 8. Conclusion. Now you're in the know. So there you have it. We've explored the fascinating world of electricity, from the flowing current to the pushing voltage and the resisting resistance. We've also learned how these concepts are interconnected through Ohm's law, and how they play out in our everyday lives. Understanding these basic principles of electricity empowers us to use electrical devices safely and effectively. So next time you flip a switch, charge your phone, or watch TV, remember the invisible forces at work, making our modern lives possible.